So for the mousetrap car project, the first thing I'm going to talk about is displacement. And you find displacement. So delta x equals final position minus initial position. And since we start with rest, my initial position will be 0. And my final position is 6.5. And this comes from our graph. So that means my displacement is 6.5 minus 0. And my change in position is 6.5. The second thing I'm going to talk about is acceleration. So for the mousetrap car, we have two different accelerations. We have our acceleration speeding up and our acceleration slowing down. For speeding up, our acceleration is 0.4437, and our acceleration slowing down is 0.7806. And this also comes from our graph. For speeding up in our force diagram, so we have normal force pulling up and our weight pulling down, and they're equal. So they're equal, and then our friction is going to the right. And when you add our forces up, our sum of forces equals mass times acceleration, which is Newton's second law. So for our sum of forces for our acceleration speeding up, it's um, 0.0798, and you get that by multiplying your mass and acceleration. So the mass of the car is 0.18, and our acceleration for speeding up is 0.44. For slowing down, our force diagram is the same, except our friction is going in the opposite direction, so it's towards our left. This time, our sum of forces will be pointing to the right. Like the first force diagram, sum of forces equals mass times acceleration. Our mass is the same, so it's 0.18, and our acceleration is different because it's slowing down. The acceleration for slowing down is 0.7806. So our sum of forces equals mass times acceleration, which is 0.18 times 0.7806, which equals negative, our acceleration slowing down is negative 0.7806. So our mass times acceleration and sum of forces is negative 0.1405. For kinetic energy, the formula for kinetic energy equals is EK equals 1 half mv squared. So our mass is 0.18, and our velocity is 1.457, or our velocity squared is 1.457. You get that by squaring your acceleration speeding up. So your kinetic energy will be 0.19105 joules. Okay, so for our energy flow diagram on the bottom left corner, so we have our mousetrap car at its initial position, so starting at rest at 0. So our E elastic is at its max, and our velocity equals 0. Our system is our car, and so when as soon as we release the spring, energy is dissipated, which leads to our kinetic energy, which was 0.19105, found in the previous equation. Therefore, our E dis equals EK plus EK minus E elastic. Okay, so for E elastic, you find that by 1 half K, which is our spring constant, X squared, which is your final position. And then you find your kinetic energy with 1 half mv squared, which we already found. Okay, so our E does, so when you find your E elastic, you get 1 half, and then K is 0.689, and you multiply that to 6.5 squared, which is your final position, and you get 14.55 minus, and then our EK is 0.1905, and it's around 14. Okay, and then okay, so the second thing I'm going to talk about is our So elastic, so that comes from the spring of the mousetrap car. So basically, okay, so your F that pi again. When you add that, you okay, so I have to re-explain the E-elastic. So okay, so your E-elastic comes from the spring of the mouse trap car, which propels the car forward. Um, okay, so basically, we found the slope of our graph is 27.17 newtons per meters, and then to find f, so f equals 27.17, which is the slope of our graph, and you multiply that to 0.06 pi, which equals 5.12, and then you add 1.09, or not the area, height of the